All right, so we were talking about structures yesterday, and we got up to looking at pointers to structures. So we had this phrase structure, arguably developed from PA4. And, well, I guess I changed it back. But we changed this so that we were passing a pointer to the structure so that we could manipulate its values inside this function called function. And so we typically see things like this. So we've got a structure called, I'll just call it my struct, and it's got some integers and maybe a name and maybe some other stuff. And then we've got a variable, I'm just calling it x, which is a structure my struct. And if we want to pass this to a function in a way that the function can manipulate it, typically we would say function and we'd pass the address of that structure. But that's not really what we want to do. More commonly, what we're going to do is define x to be a pointer to my struct. And then when we call our function, we're just going to pass x. And really, in winter, every time that we have a struct, we're going to be dealing with pointers to it. It's very rare that we're going to actually pass around an actual structure to a function. We're usually going to use pointers because we really want pass by reference. We really want a function that we hand a structure to be able to manipulate that structure's fields. So we really want an address. Yeah. Where? Semicolon. Yeah, so that's basically a variable declaration. So x is a pointer to struct my struct. So how many people remember the Malloc statement from 121? So here's the thing. All right, so there's our function that's supposed to change an argument to 12. It's called func. Our main program makes an integer I, passes it to func, prints out I. We know I is not going to change the value when we do this because I is passed by address, even though our function says to change its argument to 12. So let's modify this in a moment. Alright, so I was 0 and it ended up staying 0, even though we set it down here. So the quick fix around this is pass a pointer to an integer, pass the address of I, take the thing pointed to by arg, and set that to 12 and define arg to be a pointer to an integer. Right, so now we've got happiness. But it's going to be more common that we do the following. We actually define I to be a pointer to an integer, and then when we pass it to a function, we can just pass I. And when we want to print it out, we print out the thing pointed to by I. And this will blow up gloriously. And why does it blow up? So we're passing I to our function. Let's check the value of I. I is equal to 0. When we get into our function, we're using arg. Let's look at arg. Arg is equal to 0. That's the thing we pass to it. This is saying, take the thing pointed to by arg and set that equal to 12. Well, since arg is 0, we're trying to change the contents of memory location 0. That's not a valid location. So if we just try to look at the address, look at the thing pointed to by arg, right, it'll tell us can't access memory at address 0. So that assignment statement tries to write memory in a location that we don't have access to, and we get a signal. We talked about signals. We get a signal called seg_v. That's what a segmentation fault comes from. The memory subsystem sent us a signal. And this is not surprising because we never gave I a value. We never initialized it. And then we said integer star I, which says I points to an integer, but we didn't initialize I. So we can initialize I if we want. So now if I look at the value of I, it's 42, right, 2a in hex. And we come in here, and arg is 2a hex. But if we try to look at that memory location, we get an error. Because I initialized it to 42, but 42 is not a valid memory location either. And so if I try to make this assignment statement, I get my sig vector segmentation fault, and my program dies. So what value should we assign to I so that we don't get a seg fault? Well, it's got to point to some valid memory location. That's what Malloc is for. Malloc answers the question, where should I store this integer? So if we believe an integer is 4 bytes, we can say Malloc 4, and that'll return a location in memory. And it'll be a better location than 0 or 42. It should be a location that does not create a seg fault. So before we call this I is equal to 0, once we come back from Malloc, what's I equal to? That's good looking memory location. Well, I think it's a good looking memory location. It's a bunch of 5s and some 7s, and it ends with a 0. That seems pretty good. So we call our function, and arg is equal to that. And we can say, let's see what's stored to that memory location right now. There's a 0 there. So now if we make this assignment statement, and we look at what's stored at the location that arg points to, hey, it's got our 12. And if we next out of here and we come back and we've got our print statement, and we say go ahead and do the print statement, tells us I equals 12. Okay, so that Malloc gave us some location ending with 6260. Let's rerun our program. Let's look at I. Well, it's still 6260. I don't know what this will do. Let's try it. Let's run this again. Let's look at I. Hey, it's still 6260. Okay, it's consistent. It may not be consistent. It may be because I'm in GDB that it's always giving me the same value. But let's try this. Let's go out of GDB. I don't know if LX is the right notation or not, but I want to print out this argument I as a long hexadecimal number. Let's just print out what Malloc returned. Yeah, it doesn't like the LX, but that's okay. All right, so I run S4, and the return from Malloc was something ending with 1260. And I run it again, it's still something ending with 1260, but it's a different address. It's 5582670 as opposed to 557. And every time I run this, I seem to get a different number. It seems to consistently end with 260. So we don't know what value Malloc is going to give back to us, but we don't need to know what value it's going to give. All we need to know is that it's going to give us the location of somewhere valid in memory where we can store, in this case, 4 bytes, because we said Malloc 4. Now, in the case of this, my structure, and we set up X to be a pointer to my structure, again, if we try to use, say, the thing pointed to by X, and pull off the name field, we're probably going to get a seg fault because we haven't given X a value yet here. So we need to have X point somewhere in memory. So before we can use X, we're going to want to say X equals Malloc. And Malloc, you have to tell it how many bytes you want to allocate. Well, if we know integers are 4 bytes, this would be 12 and this would be 120, so probably 132 bytes would work, but maybe not. Right? Maybe integers this week are 6 bytes, or 8 bytes, or 2 bytes. And sometimes computers like to do what we call word aligning things. For example, suppose we had a character in the beginning here. Character takes 1 byte. Theoretically, we could store X in those next 4 bytes. But no compiler is going to do that. Because it turns out that integers work best when they begin at an address that's a multiple of 4, or possibly 8. So if this was stored at location 1260, if we did this, X would begin at location 1261. That's going to kill your performance. Right? Memory management systems like things to be word aligned. And a compiler will know that, and it will actually set this up as follows. It will store C at location 1260. And the next 3 locations, it'll just leave blank. And then at location 1264, it would store X. And we don't need to know all these details ourselves, but to know how many bytes we need to allocate for a structure, someone needs to know this. Well, the compiler knows it, right? So the compiler, we do something like this. We say whatever the size of that structure is. I forget what I call it, my structure. Allocate that many bytes. And it will go ahead and calculate at compile time how much memory it needs for this structure, and then Malloc will malloc that many bytes. So this other program, we had a structure phrase defined. It had 120 characters, 2 integers. Let's just make one line of our main program which just says print out the result of calling size of struct phrase. And let's see how big that structure is. Why doesn't it like that? The special runner type input has type line. Oh, I don't care about that. Okay. So we'll go with that, and it tells us the size of a structure phrase is 128. And we might have guessed that because we had 120 elements in our character array, and then 4 bytes and 4 bytes. That's 128. So let's make our array 119. And it tells us the structure still needs 128 bytes. That's that word alignment. All right, it's not going to start count right after the 119th character in the phrase because it's not word aligned. In fact, if we make it 117, it's still going to take 128 bytes. If we make it 116, now it takes 124. $117 takes 128, so let's try this. Let's just change the definition of the structure to put the character array at the end. I don't know what it's going to do. It's still 128. But we don't need to know this, right? And in fact, we don't want to know this. We never want to malloc a particular number of bytes unless we have a really, really solid reason for saying I only want, 17 bytes. In general, we want enough memory to store some kind of variable, and we want to use size of to tell us how big that variable is. And if it's a structure, we want to use size of the structure rather than adding up the fields. All right, in malloc, you should include standard lib, so you don't get all those compile errors. And it technically returns a pointer to void, so you get some warnings with that. So the flip side of malloc is free, because what does malloc do? It's looking for memory locations where you can, store some stuff. Where do those come from? Well, there's something inside the system called a heap. And the heap is basically a big pool of storage. It's where most of your storage is. And when you call malloc and you say, give me 150 bytes, it goes into the heap, which has got all kinds of information about it, and it looks for some chunk of at least 150 continuous bytes that it can give to you. And when it finds that, it will give you the address of the first byte, but it also has to update some information so that if somebody else wants memory, it doesn't give that same memory to somebody else. Because you don't want to start storing variables in memory and have somebody else storing things in the same location. Right? It's like trying to share a whiteboard with your housemate. So the system marks memory when it's in use. Okay, it effectively takes it out of the heap. And that's great as long as you want to use that memory. But if you're done using the memory, you really want to tell the system that you're done using it so that it marks it as being available again. Otherwise, it thinks you've still got this memory in use, and if you run your program for too long, eventually you might run out of memory. Right, so whiteboard example, you're doing 215 problems on the board, so you say, malloc, here's my section of whiteboard, nobody else can use it, right? And that's great, but if you leave at the end of the day, and you don't tell whoever keeps track of the whiteboard that you're done with it, the next day you come in and you say, I want some whiteboard, it's going to say, well, that's in use. Here, you can use this spot. And you do your work there, and you go home, and the next day you come in and you say, I want some whiteboard. Well, those spots are in use. It's going to say, okay, well, you can use this spot. Eventually, you're going to ask for some whiteboard space, and it's going to say there's none available. It's all in use. Okay? So that's what happens with calls to malloc. So you call free to basically say, I'm done with this resource. And if I malloc this and I use it and then I free it, and then I come back later and I say, hey, give me some whiteboard space, it'll say, oh, this is free, here you go. But it's really easy when you're writing code, because we malloc stuff all over the place. It's really easy to malloc stuff without freeing it when you're done. And that gives you what's called a memory leak. So when you have a program that the longer you run it, the lower your system memory becomes, it's probably got a memory leak. And large programs, this is really easy to have happen. And some pretty mainstream commercial programs have been notorious for having memory leaks. And periodically you just had to exit out of them and restart the program. And when you exit a program, the memory that you've allocated gets freed automatically. But if you open a browser window and you leave it open for 2 weeks, sometimes your memory just keeps dropping and dropping and dropping, and your performance goes down, and eventually you can't do anything on your laptop. And if you do a memory scan, you see that you've got 16 megabytes of memory free or something. And then you just kill that one program, restart it, and everything's great. So we'll deal with this a fair amount in 222, because we'll be doing dynamic memory allocation. Fortunately, there's tools to help you find memory leaks, and the main tool that we'll use is something called valgrind. And basically, you run your program through valgrind. When you're done, it tells you if you had any memory that you allocated but forgot to free. And it can help you pin down those kinds of leaks. And again, a program that you're just going to run and exit, you got a high-low program or something, it's not a big deal. It's more a program that doesn't exit, like a web server that theoretically could be running for a few years. And if that's consuming, an extra 1,000 bytes an hour, it's going to run out of memory pretty quickly. All right, so let's go back to S1. So we had a pair of integers and the phrase, and we made a structured phrase P, and we set up some fields, and then we passed it to our function. So let's play with this a bit in GDB. Alright, so we're going to set P's count field to 5. Let's print out the value of P first of all. And GDB understands your structures if you compile with a G switch. So it tells us P has a count field which is 0, a location field which is 0, and a the phrase field which is all of this stuff, 32 nulls, a 377, a 265, and so on. So we're going to set p.count equal to 5. And now if we print the value of p, that count field has changed. All right. So this is where GDB is really going to be your friend, because it knows about how you wrote the code. You're not just looking at bare memory, right? It knows what the fields are and so on. So let's string copy hello into the phrase, and now let's look at p again, and it looks exactly like what we expect. Right, 5 and 12 for the integers, the phrase is hello, followed by actually 26 null terminators, and then some gibberish and some more nulls. Now if we look at the address of P, it's at this location, so something ending with so a bunch of 7Fs and then ending with E4, C0. All right, we're about to call our function P, so let's step into that. And we call this with an argument, and if we print arg, right, it's got the same stuff that our original P had. Right, and even though our phrase contains hello, with a null terminator, all this other gibberish is also the same as what it was in our main program. Okay, it copied the value of our argument and passed that value. But if we look at the address of this argument, it's different. It's something ending with E440 as opposed to E4C0. And this is the reason that when we change p.count, we're not changing, when we change arg.count, we're not changing p.count, right? Because arg is pointing to some different spot in memory. So let's just step out of here. Okay, so we're back inside main. So P hasn't changed. All right, so P is E4C0. Let me get fancy on here. All right, so P is at E4C0. We can print the address of p.count and it tells us that's E4C0 also. If we print the address of p.location, that's E4C4. And if we print the address of p.the phrase, that's E4C8. So our structure looks like it's stored in memory like this: count followed by location followed by the phrase. And those things are packed next to each other. So let's rearrange our structure definition with the phrase in the beginning again. So P is stored at E4C0, so that's still fine. P.count is stored at E538. And P.loc is stored at E5.3c. And P.the phrase, that's the one that's actually at E4C0. Right. So it's storing the structure in memory based on how we defined things in the structure statement, which isn't really surprising. So here we defined the phrase first, followed by count and loc, and that's how it packed it into memory. But that's not guaranteed. Okay, we never want to count on that, but we don't need to count on that, because we generally don't access fields other than by the field name. And the compiler knows where it stored count and loc in the phrase, and so if we say structure variable dot count, it will know where to find that relative to where the structure starts. But this can bite you if, for example, I'm writing my code in different files, and in one file I define my structure like this, and in a different file I define it like that. Those structures won't work together very well. And the compiler probably won't notice this. especially if I compile separately. Okay, so let's just clean this up and look at it. What's my best bet here? Let's do S4. All right, so let's look at the example we already did of where we're passing the address of a variable. And let's just break that down in GDB. So we'll say start. We're going to set I equal to Malloc 4. So before we do this, I is 0. Once we call Malloc, I is equal to that big long thing. Ending with 6260. So we're passing that to our function. I should have said step. Alright, so there's the address of I. Let's go ahead and step into our function. So our argument is still that same number, bunch of 5, 6260, right, because we passed by value. And the thing at that location is a 0. But once we set it equal to 12, right, the thing at that location has been changed. But here's the thing. If we look at the address of our argument, it's 528. If we look at the address of I, which we passed, it's totally different. It's 548. So our main function passes I to func, and func takes an argument which we call arg, right? This variable and this variable are not the same variable. They're stored at different locations. Okay, I is stored at location 548, arg is stored at location 528. That's okay, because we're not trying to change arg, we're trying to change the thing pointed to by arg. So when we call func I, we pass the value of I, right? We're not passing that 548, right? We're passing the thing that I points to. And so down here, we take the thing that that points to, which is the thing that I points to. If we change that, then we've changed the thing that I points to. So that's why we get values back that we change in our function. Okay, so it's still passed by value, but the value we're passing is an address. That's sort of the punchline. But if you really dig deep, right, you realize that's a pointer to an integer. But don't go there, unless it makes you happy. All right, so I equals 12. So again, we're going to go through all this in careful detail starting in 222, okay? But I want to kind of get our brains going in this direction ahead of time, because we're going to kind of hit the ground running, even though we're starting from first principles. So we got a structure cool. It's got some integers. It's got a name, which is a string, and so on and so forth. This would be pretty weird. If we could put a field in there called which was itself a structure cool, that's going to freak out the compiler. This is kind of a recursive thing we're trying to do here. We're trying to say that so what are the rooms in a house? Well, there's a kitchen, and there's a bedroom, and there's a living room, and the living room contains a house, right? And so what are the rooms in a house? Well, there's a living room, and there's a bedroom, and there's a kitchen, and the living room contains a house, right? And we're as soon as we do this, we're basically making an infinite nesting of these structure cools, and that's not feasible. But here's what we can do. We can say that a structure cool includes a pointer to a structure cool. That's perfectly legal. There's no sort of infinite recursion required to grapple with this. We're saying there's 3 integers, there's 10 characters, and there's a memory address. There's a pointer. It happens to point to a structure cool, which is what we're defining, but that does not cause any problems. It could be a pointer to an integer, a double, a character, a structure cool. Doesn't matter. All the compiler needs to know is this is a memory address. The programmer, that's you and me, needs to worry about the fact that this is pointing to a struct cool, even though it's inside a struct cool. But we'll have good reasons for doing that, and we'll be able to manage that. So this is the other reason why we tend to have pointers to structures, is because we can put them inside structures. So here's the first structure we'll be working with in winter. Something called a node that has 2 pieces of information, an integer called data, and a pointer to another node called next. And these nodes will build something called a linked list. And a linked list will be the first sort of real data structure we deal with in 222. And it's like a glorified array. It lets us do what we do with arrays, but much more efficiently in terms of inserting and deleting from the middle of an array. And it will have this kind of peculiar looking notion that part of what's in this structure is a pointer to another structure. But it's not going to actually point to itself usually. It's going to point to a different struct node. So we'll have one struct node sitting here, and it'll have a piece of data, and it will have a pointer which is going to actually reference a usually different struct node with possibly a different piece of data and possibly a pointer to a still different struct node, and so on. And we'll chain these things together and make a big long list of them, and it'll be a really cool way to organize information. And then we're off and running, and this will lead us into trees, and that'll lead us into all kinds of other things. And before you know it, winter quarter will be over, and we'll be doing Java. All right, so not on the exam, nothing you need to know before 222 starts, because we're going to go through all of this in careful detail in winter. But just kind of a preview of where we're going, just to sort of like be thinking about in the background. So tomorrow, let's start doing review. Right, we got 2 days. So study guide has been on Canvas for a while. Go ahead and look at that. Bring questions if you have them. Otherwise, we'll just start going through it, and we'll just talk about it. And probably don't need 2 days, but I'll allocate 2 days anyway. All right, so I'll see you next time.